All right, in section 8.3, we're continuing to talk about hypothesis testing, which has been all of chapter 8. Chapter 9, actually, our last chapter before the final exam, also deals with hypothesis testing, but it adds back in chapter 7 with the confidence intervals. So, really, we're doing a lot of repetitive learning where we have similar ideas to what we've previously learned. So, when we are testing a claim about a mean, we have requirements when our sample or when our population standard deviation is not known, which, as I said in previous sections, I believe in 8.1, usually it's not. Because why would we know the population standard deviation and not know the population mean is the thought. So this is a very rare case. So usually it isn't known. And when it isn't known, we require that the sample be simple random. The population must either be normally distributed or n must be greater than 30. So if it says something about the population being normally distributed, then we're good to go. It doesn't matter what the sample size is. If it doesn't say that, then we need n to be greater than 30. So here is the formula to use for test statistic. The T, it's the same one we used before if you're calculating by hand. If in the very rare case, and I don't know why I keep doing this, but if the population standard deviation is known, which would be very rare, then that's when we would use Z, and then we would have this formula here. So in this section, we are going to be using one of the tables, which we haven't used tables a lot in this course. We've relied mostly on our calculator. But this one we need to just at least make you familiar with what this table A3 does. So what table A3 does is it gives us a range of values for our p-value. And of course, the p-value is one of the ways that we can decide whether we want to reject or fail to reject our null hypothesis. So the claim we are testing in part A is that the tar amounts in king-size cigarettes, the mean, population mean, is greater than 20.0 milligrams. The sample size is n equals 25, and the test statistic is t equals 1.733. So if you want to write out steps for this, maybe that might help you. The first thing that we're going to do in table A3, which is in the back of your book, I'm going to bring one up on the screen here in a minute once we're ready to actually use it. But first thing you're going to do is find the row that corresponds to the degrees of freedom. Then that gives you the row. The next thing you're going to do is find where your test statistic would fall in the rows, because the rows on the table are going to have actual values like the test statistic. So you figure out, okay, where in this number line of values is my test statistic ending up. Then once you do that and you found where it would fall, you follow that location from step 2 up to the top of the chart and choose one-tailed. And that's if it's a less than or a greater than, because both left and right-tailed are one-tailed, or two-tailed, which would be for a not equal, to find the range. And again, sometimes the steps don't make sense until we actually look at it. So here, the information that we need is that our sample size is n equals 25. So that means that our degrees of freedom would be 24. And then we need to know that our t, our test statistic, is 1.733. So I'm going to bring up the table now. Of course, it's really big. Let me resize it here so it fits. So I looked down, degrees of freedom 24. My test statistic was 1.733. So I'm going to go through here. It's definitely smaller than all of these, smaller than all of these. Okay, it is bigger than this guy. It's bigger than 1.711, but smaller than 2.064. So that means that when I go to do the part where I follow it up, I'm following it up in between these two. Now, this was a one-tailed because the claim was mu greater than, which is just a right-tailed test. So I go to one tail. The two values where I landed between are 0.025 and 0.05. So that means that my p-value falls between those two numbers. All right, let's try it again just to make sure you understand. So here, the claim we're testing is that for measurements of standard head injury and car crash tests, mu equals 475. The sample size is n equals 21. The test statistic is t equals negative 2.242. So sample size is n equals 21. That means my degrees of freedom are 20. Because my claim is mu equals, that means that my null hypothesis is going to be the equals, which means the alternative is a not equal. So since this is a not equal, that means it's going to be a two-tailed test. So degrees of freedom 20, test statistic negative 2.242. So go over to the table, degrees of freedom 20, and if it's negative, we're pretending that these are negative. It works that way as well. But be careful because, negative works the opposite way with less than and greater than and whatnot. So negative 2.242. So let's see. It's definitely smaller than this, smaller than this. So here it would be between negative 2.528 because we're pretending these are negatives. That's what you do when you have a negative test statistic. So my negative 2.242 would fall between these two guys. So I follow it up. It's two-tailed, so make sure I use the two-tailed area, and it's going to be 0.02 and 0.05. So that means in this case, p-value is between 0.02 and 0.05. Now, something that happens sometimes that I want to make you guys aware of, even though it's not in one of the examples, sometimes your test statistic, let's say that for degrees of freedom 10, my test statistic was 3.5. That's bigger than everything in here, which means that it would be on the left side of this. So if I follow this up, notice that the values get smaller on the left side. That would mean that I would write p-value less than this right here. Same thing if you were doing degrees of freedom 10 and your test statistic was 1.1, that's below this guy here. And so you would say, okay, well, p is greater than, whichever one of these, depending on the tail. So it's not always, I call these inequality sandwiches where I've got a limit on each side. It's not always a sandwich. Sometimes we end up with a strictly less than or a strictly greater than. Okay. Really, that's the only part that is new per se, because example 2 and example 3, we did similar things to this in 8.1, not necessarily with this guy as much, but we are now just going to run through all of the steps. If you look at the front of those 8.1 notes where I've got the flow chart of your steps that you should be taking for hypothesis testing, this is what we're going to do. It's just that in this section, 8.3, we're strictly using a mean, which tells us that generally we're going to be using T unless our population standard deviation is known. The only time we use Z is if we know the population standard deviation. Okay, so let's read example 2. In a sample of 40 Chips Ahoy reduced fat cookies, the mean number of chocolate chips was 19.6, and the standard deviation was 3.8 chocolate chips. Use a 0.05 significance level to test the claim that Chips Ahoy reduced fat cookies have less fat because they have a mean number of chocolate chips that is less than the mean of 24 for regular Chips Ahoy cookies. So we do not know the population standard deviation. We have a sample standard deviation. So that means we are going to be using T here. Remember that we want to write out all of the steps. In your homework, you absolutely must, on problems like this, have everything written out. So look back at those 8.1 notes to make sure you're stating everything. So claim in symbolic form would be that the mean, don't use P because we've got mu this time, is less than 24. So mean less than 24, which means that that becomes our alternative hypothesis, our null hypothesis. We always want to have the equal. So mu equals 24 for that, mu less than 24 for our alternative hypothesis. I know that my alpha is going to be 0.05. I also know that this is a, because it's a less than situation, that this is going to be a left-tailed. So I'm going to do both p-values and critical values here. Again, in your homework, unless it specifies, you can choose. You can just do one or the other, but I think it can't hurt to just make sure that you know how to do both. Again, so on a left-tailed test, that would mean that that alpha area is only on the left side. Because this is a T situation, use inverse T, not inverse norm. So inverse T of 0.05 with, I have to enter the degrees of freedom. So my sample had 40, so that means my degrees of freedom would be 39. So inverse T of 0.05 with 39 as my degrees of freedom gives me T equals negative 1.68. So this is my critical value, which I'll need if I'm using that method. So here's my critical value. So label that. Then I am going to run the test. Now, certainly you can calculate the test statistic by hand if you want to. And if it specifically asks you to do that, then use the formula. But if it doesn't specifically ask you to, why would you spend more time than what is needed when we could just use the calculator? So I'm going to bring up my calculator. Maybe. Hold on a second. All right, so since we are using the T statistic because we don't know the population standard deviation, that means in our calculator, when we go to stat tests, we're going to choose choice 2 for T test. And like our other T values, when we did the T interval in chapter 7, it gives you the choice between data and stats. Here we have stats because we don't have the actual data from the sample. So mu sub 0 is whatever number is part of the claim. and part of your null and alternative hypotheses. So in this case, it's 24, since our claim is that mu is less than 24. So enter that in mu sub 0. Then we will enter the other statistics that we were given. So in this case, we have our x bar, which is the sample mean, our SX, which is the sample standard deviation. And so we just enter all of that information that they give us. So once we have that, make sure you're selecting the right type of test. In this case, it's a less than, because it's a left-tailed test. And then scroll all the way down, maybe. Sorry, I had to restart this calculator and it's being, oh no, come on. It's being a little fickle. Okay, go down to calculate. And that is going to spit out for us several different things that are of use to us. So up at the top, it just reiterates what our claim was. Then it gives us this guy as our test statistic. So negative 7.32 if we're rounding to 2 decimal places. Be careful on this p-value, because if you just look at the beginning, you're going to write 3.873. But look at what's after it. It says e to the negative 9. So this is 3.87 times 10 to the negative 9th power. So that essentially is 0. Now remember that we're never ever going to write 0. So I'm going to write out what our calculator work was. So we went to t-test and we entered our 24, and then I forget what order it was in. I think that the next thing we entered was the mean, then the standard deviation, and then the n, I believe, and then we chose the less than. So this is what you would write out for your work for doing the t-test, and then that gives me that my test statistic is t equals about negative 0.732, we said, and my p-value, you don't have to write out the whole thing because it's essentially 0, but don't write 0, write 0 plus, it's just barely bigger than 0. So that means that I'm going to explain with both methods here. So remember that with the critical value method, that the rejection region would be right here. So anything that is to the left of this negative 1.68 is going to be in the rejection region. Negative 7.32 is definitely to the left of negative 1.68. So it is in the rejection region, which means that we're going to say that we're going to reject our null hypothesis. If we were using the p-value method, remember we would compare the p-value to our alpha value, and 0 plus is definitely less than 0.05, so we would get the same conclusion, that we would reject h sub 0, our null hypothesis, which means our claim does not include equality, it's a less than, and we rejected, so that means we say there is sufficient evidence to support the claim that Chips Ahoy reduced fat have a mean number of chocolate chips less than 24. Whew. I know it gets tedious writing this out, but it really is standard procedure for hypothesis testing that we need to write out in that very specific format. All right, last example here, same idea as what I did in example 2. I'm going to use both the p-value and the critical value just to illustrate both. But this time we're given the data instead of the statistics. So it says listed below are brain volumes in cubic centimeters of unrelated subjects used in a study. Use a 0.01 significance level to test the claim that the population of brain volumes has a mean equal to 1100 cubic centimeters. So this means that our claim, remember, be very careful to use the right variables, is that mean is equal to 1100. So equal is always the null, so that claim is our null hypothesis as well. Our alternative hypothesis then, whenever our claim is an equals, our alternative is a not equals. We know that we're using alpha equals 0.01 here. So if I am finding my critical values, to use that method, I know that because it's a not equal that this is two-tailed, so my alpha needs to get split between both sides. So 0.01 divided by 2 is 0.005 on both sides, which means that there's 0.99 in the middle. So you can either do inverse t of 0.005, which is going to give me this guy right here, with degrees of freedom 1 less than n, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 pieces of data, so degrees of freedom would be 9. Or you can do inverse t of 0.995 with 9 as your degrees of freedom. That would give me this critical value here. Remember, it really doesn't matter which one you do, because when it's two-tailed, we should end up with the same thing. We just have to do a plus or minus. So it doesn't matter which one we do here. If I do inverse t of 0.005 with degrees of freedom 9, you can see that that gives me maybe negative 3.25 approximately. If I were to change it and do the inverse t of 0.995, just to prove to you, and run that, we get the same thing, only the positive. So remember, you don't have to do both. That's why I write an or, because it should be just the plus and minus on it. So this is our critical value. And now we can run our test to find our test statistic. So go back to my calculator. Stat tests. Oh, never mind. Can't do stat tests yet because I haven't entered my data. So I'm going to clear out my list 1 here and enter the data that's there. So remember to be super careful with the entering of the data after you have it in there. You always want to double check it, because if you press, one little button incorrectly, then you're going to end up with everything wrong about your values that you're looking for. So 1070, then 1173, 1067, 1347, 1100, and 1204. Okay, so I'm going to go through and double check them real quick just to make sure I entered everything correctly. That looks good. So now I can go to stat tests, choose my t-test again, because I was not given the standard deviation of the population. Go to data this time. Mu0, remember, is whatever number is part of the claim. So in this case, it's 11. Oops, see, talking about typos, and I Did a typo there, 1100. My data is in list 1. If it's not, make sure you change that. Frequency always stays 1. The alternative was a not equal. It's a two-tailed test. Scroll down to calculate. And then that gives me my test statistic and my p-value. Notice this time my p-value is not in scientific notation, so that's helpful to us. So I've got 0.81 for my test statistic, 0.437 for my p-value. So I did t-test, and I did data this time. My mu sub 0 was 1100. And then what else did I enter? I've already forgotten what else I had to do. I did L1, frequency 1, and I did not equals. And so my test stat is t equals 0.81. The p-value that my calculator gave me is 0.437. All right, so now if I'm making my decision, if I'm using the critical value method, my test statistic is positive, which means I would be referring to the positive critical value. In order to be in the positive rejection region, I would need it to be above 3.25. This is not, which means that critical value method is going to tell me to fail to reject. So now I check if I were using the p-value method to make sure that lines up. Here's my p-value. Here's my alpha. My p-value is not less than my alpha, so those do give me the same conclusion in that I want to fail to reject my h sub 0. So in this case, sorry, dog barking, because I have failed to reject, that's going to give me the not sufficient evidence. Because my claim did include equality, that means I'm going to use warrant rejection. So my final conclusion is there is not sufficient evidence to warrant rejection of the claim that mean brain volume is 1100 cubic centimeters. All right, now one thing to keep in mind before we end here is just on the next quiz, which is just this section, it's all mean values. In that if they asked a follow-up question here, it did not say anything about the population being normally distributed, and I only have 10 pieces of data. So technically, really, I have not met requirements to do a hypothesis test and have my results be valid. So that's one important thing to make sure you're always paying attention to, because sometimes in the homework they try to trick you. The other thing to keep in mind is that on the quiz that's just 8.3, everything is mu. But keep in mind that when we get to the final exam, everything's mixed together. And it's really important that you use the right variable, because very often, I wouldn't say it if I hadn't seen it a lot, very often I'll get people writing p less than 24, p equals 24. And obviously that's a small deduction, but it is a deduction every time you do it. So make sure you're paying attention to what exactly our claim is saying so that you can use the right variable. All right, I think that's it for testing claims about a mean.